As you already know, we define work in two ways. One is very mathematical with this formula that says work is equal to the integral of the dot product of force and incremental displacement. However, if force is constant, then it comes out of the integral sign. And of course, the integral of ds is just delta s. So in cases where force varies over the displacement, we use what we'll call version number 1. But if force is constant, we can simplify and use version number 2. And of course, in version number 2, this has the same result as the magnitude of the force times the magnitude of the displacement times the cosine of the angle formed between those two vectors. I realize we have not used the formula in this form yet, but that'll come up in the next couple of lectures. Okay, the second definition of work is it's equal to some change in energy. Well, that doesn't really help if we haven't properly defined what energy is. So energy is a quantity that's conserved in our world. Certainly you've heard of that idea of the law of conservation of energy. Energy is measured in joules, and energy can appear in many different forms. So think of this box that I've drawn here as all the different forms of energy. We're going to divide that in two. We're going to say there's basically two main categories of energy. There's useful energy, or maybe we'll call it harnessable. Actually, the word we use for this is mechanical. And then there's wasted energy. Often wasted energy appears in the form as thermal energy, which is, simply put, the random kinetic energy of the molecules in a substance. Mechanical energy itself can be broken into a couple different forms. There's energy of motion, and there's stored energy. So think of something like a compressed spring, and you attach a block to it. When you release the spring, then it's going to set that block into motion and therefore convert stored energy in the spring into the kinetic energy of the block. Oh, so that's the word we use for this quantity energy of motion. We call that kinetic energy. Stored energy is often referred to as potential energy. The symbol we use for kinetic energy is just a capital K, and the symbol we use for potential energy is a capital U. Well, we're going to reserve our study of potential energy for the next unit of study 3.2. But here in unit 3.1, we want to do two things with this quantity or concept of kinetic energy. One, come up with a formula that tells us how we can calculate an object's kinetic energy, and two, express this concept known as the work kinetic energy theorem. So let's get into it. Let's see if we can derive the work kinetic energy theorem, and along the way come up with an equation we can use to calculate an object's kinetic energy or energy of motion. So here's an example of a block that's being pushed up an incline or pulled up an incline by an applied force Fa. And then there are all these other forces acting on the block that you can't escape. The ramp pushes against the block. We call that normal force. Gravity, of course, pulls straight down. And if the ramp and the block have any roughness between the two of them, there will be a frictional force opposite the motion. So in this case, we're assuming that the block has motion toward the top of the incline and therefore displaces some distance upward. We can say the incline is an angle theta. So if we make a free body diagram for this block, we can resolve the applied force and the force of gravity into their vector components. So the displacement becomes the x-axis. We always want to make the x-axis the axis for the displacement. The reason for that goes back to our definition of how we calculate work using this dot product. So if we define the x-axis as the axis of the displacement, then the displacement vector has no components other than an x component. The displacement vector will have no y component, and the force then would need to be broken into x and y components. So this, of course, is a resolved free body diagram. We're already showing all of the forces along the x and the y-axis. So there's a force of friction plus mg sine theta pointing down the negative x-axis, and there's the applied force times the cosine of some angle. Now, I'm not going to call that angle theta because the angle between the force and the displacement isn't necessarily that same angle theta. This could be a different angle. Maybe we call it phi. So this would be FA cosine phi. Okay. And then normal force along with the other component of the applied force, FA sine phi, point along the y-axis. And then we have mg cosine theta pointing on the negative y-axis. But in the end, I think we'll all make the assumption that if the object exclusively moves along the x-axis, that there's no acceleration along the y-axis. So normal force plus FA sine theta has to be just as great in magnitude as mg cosine theta, so that all the forces along the y-axis cancel one another out. So now you're left with a larger amount of force in the positive x direction of F cosine phi and a smaller amount of force due to friction and mg sine theta back the other direction. And so we can make one single overall amount of force that simply points in the direction of the positive x-axis, and I'm sure you can come up with some sort of algebraic expression based on these, but we don't need to actually name this vector. So in the end, what we could just say is this represents the net force. Okay, now the net force is equal to, well, I'll say it, but I won't write it. It's equal to the quantity I just highlighted in yellow minus the quantities I just highlighted in purple. Okay, but regardless, that's just some net amount of force. Okay, well, where does that lead us? So the net amount of work done should be equal to the net force dot product with the displacement. Displacement's a vector, net force is a vector. However, because we've made a net force that points along the x-axis in the same way that the displacement is defined as being parallel to the x-axis, that means this would be written as the magnitude of the net force times the magnitude of the displacement times the cosine of the angle between them, but based on the way we defined our x-axis, we have a guarantee that that angle is going to be 0 degrees, and as we know, the cosine of 0 degrees is just 1. So the net amount of work is equal to the net force multiplied by the displacement. And by Newton's second law, what can we replace with net force? MA, right? So the net amount of work done is equal to the mass of the block times acceleration times the displacement up the incline. All right, now let's think about some kinematics here. If the object starts out in position A and slides a displacement delta S until it reaches position B, maybe it already started out with some initial velocity. There's no guarantee that the object was already at rest when the applied force started acting on it. It could have had an initial velocity, and by virtue of accelerating up the incline, it's going to have some different final value of velocity. So at this point, this study of kinematics that at once was challenging is probably second nature by now. I think you've committed to memory all of these equations, and ideally you recognize that this formula would apply in this case, right? If you look at the diagram we're given an initial velocity and a final velocity and a displacement, and in our previous line of work we stated some acceleration, but nowhere in our work have we referenced any time value. So if we wanted to try to apply a kinematics equation, we can make a substitution. We can substitute out for acceleration in this line of work if we're willing to rearrange this equation. And this equation would yield an expression for acceleration that says A is equal to v squared minus v initial squared divided by 2 delta s. Or actually, we don't even need to just substitute for A alone. How about we do this? If we go back into our work, we could actually substitute for the entire product of A multiplied by delta S. So let's write it this way. A times delta S would be equal to v squared minus v initial squared. Okay, so what we had is an expression based on the definition of work as a dot product, that the net amount of work is mass times acceleration times displacement. The net amount of work is mass times acceleration times displacement. But acceleration times displacement can be substituted. So the net amount of work will be equal to mass, I'm sorry. Did you catch my mistake? I forgot. Divided by 2. I forgot this 2 here. There we go. Okay, so the net work is mass times the quantity v squared minus v initial squared divided by 2. And I'm going to distribute the m and the divide by 2, so we get the net amount of work is equal to 1/2 m times final velocity squared minus 1/2 m times initial velocity squared. Now I want to back up to this conversation about different forms of energy and remind you that one of our goals was to come up with a formula that we can use to define kinetic energy. Well, because kinetic energy is energy of motion, it certainly should be a function of the speed of an object. Things that move slowly have less kinetic energy. Things that move quickly have more kinetic energy. So kinetic energy should definitely be a function of speed. Kinetic energy is also a function of mass. Very light objects in motion don't carry as much ability to do work as more massive objects moving at the same rate. So I'm just going to make a definition, and it'll be very convenient here. Well, actually, I'm not creating this definition. This is how kinetic energy is defined. So when I write equal to with 3 lines in the equal sign, I'm saying equal by definition. We're going to define kinetic energy as being 1/2 times an object's mass times its velocity squared. And there you have it. So kinetic energy is a scalar quantity. And if that is the definition for kinetic energy, then we can rewrite this equation as net amount of work is equal to, well, I guess this would be nothing more than some final value of kinetic energy, and this would be nothing more than some initial value of kinetic energy. Or in other words, the net work done on an object is equal to that object's change in kinetic energy. That idea is known as the work kinetic energy theorem. And we could write it another way. We can say the net amount of work done on an object is equal to the change in the quantity 1/2 mv squared. Now let's think of the special case of an object that starts at rest. If an object starts at rest, the initial velocity is equal to 0, and therefore the change in kinetic energy is the same thing as an object's final kinetic energy. So we don't have to invoke the symbol delta. So if we had a problem where we had to find what is the final velocity of an object that starts from rest, as long as we knew how much work was done on that object, it should be very straightforward. Do some algebra. Let's multiply both sides of the equation by 2. So 2 times the net amount of work is equal to mv squared. Divide both sides of that equation by mass. In the end, with one more step of algebraic work, we can easily show that an object's final velocity, if it starts from rest, should be equal to the square root of 2 times the net amount of work done on it divided by its mass. All right. In upcoming video lessons, you'll see how we can apply this equation.